What if the most advanced winter survival system in human history wasn't designed by modern engineers, but by people who had no blueprints, no electricity, and no machines, only wood, stone, fire, and necessity? More than 1,000 years ago, Northern Europe faced winters so brutal they rewrote the rules of survival. Snow buried roads, rivers froze solid, daylight vanished for weeks. And in the early 13th century, written records describe something deeply unsettling. Heavily armed crusader forces, protected by massive stone castles and the most sophisticated military engineering of their age, froze to death in place. Thick walls, constant fires, endless labor, and still failure. At the same time, only a short distance away, Scandinavian communities endured the same winters without collapse. Families slept through months of darkness. Children were born. Food was preserved. Daily life continued not in fortresses, not in stone towers, but inside simple wooden structures. No furnaces, no insulation foam, no chimneys engineered by modern science. Just timber, earth, and carefully controlled fire. This contrast shouldn't exist. By every modern assumption, stone should outperform wood, complexity should outperform simplicity, technology should outperform tradition. And yet, the archaeological record tells a different story, one that refuses to stay buried. When researchers began excavating beneath frozen soil, beneath collapsed roofs, and centuries of sediment, they uncovered evidence that forced architects and engineers to confront an uncomfortable possibility. What if we've misunderstood winter itself? What if survival isn't about overpowering cold, but about cooperating with it? Because long before modern heating systems failed, long before power grids collapsed, someone already solved the problem of winter and did it so well that their solution still challenges us today. Stone castles were built to project dominance. They rose above valleys and rivers as symbols of authority, permanence, and control. Thick walls, narrow windows, endless stone. In theory, they were meant to protect their inhabitants from every external threat. But winter was not an enemy stone could defeat. As temperatures dropped, castle walls turned against the people inside them. Stone absorbs cold slowly, but once chilled, it releases that cold without mercy. Moisture seeped into pores and joints, condensing on interior surfaces. Walls sweated, floors stayed wet, fires burned day and night, yet warmth never settled. Smoke lingered in enclosed spaces. Heat rushed upward and vanished through high ceilings and crude vents. What remained was damp air, toxic fumes, and bodies under constant stress. Carbon monoxide accumulated. Respiratory illness spread. Infections followed. Medieval records describe soldiers sleeping in armor, shivering beside fires that never truly warmed the room. Castles designed to withstand siege became winter traps, places where survival quietly failed. And yet, nearby, something very different was happening. Viking longhouses, often dismissed as crude or primitive, did something stone architecture never learned to do. They responded, they adjusted, they changed behavior as conditions changed. As the outside world grew colder, these wooden structures became more efficient, not less. Heat stayed low and close to the body. Air moved where it was needed. Moisture was controlled rather than trapped. Fires were smaller, but smarter. Warmth lingered after flames died. This defies modern intuition. Buildings are supposed to lose efficiency under stress. Cold is supposed to overwhelm simple materials. Complexity is supposed to win. But Viking longhouses followed a different logic. They didn't fight winter with brute force. They reshaped how winter moved through space. The colder it became outside, the more tightly the structure worked inside. That detail alone should not exist. And yet, excavation after excavation confirms the same truth. When medieval advanced architecture failed, these so-called primitive buildings adapted and kept people alive. The excavations at Borg, in northern Norway, were never meant to challenge modern engineering. They began as routine archaeological work, mapping post holes, cataloging timber fragments, documenting collapsed roof lines buried beneath centuries of frozen soil. To the untrained eye, it looked like the familiar aftermath of decay. Nothing extraordinary, nothing revolutionary, until researchers decided to test the wood. Preserved timber samples were taken into controlled environments and examined using thermal imaging and materials analysis. At first, the results were dismissed as error. Sensors recalibrated, samples rechecked, procedures repeated. The data refused to change. The insulation performance of Viking-treated wood rivaled modern construction materials. In some tests, it exceeded them. University laboratories across Europe replicated the experiments independently. Different samples, different methods, same outcome. Then came the detail that unsettled everyone involved. As temperatures dropped, the wood didn't lose efficiency. It gained it. At lower temperatures, conditions that cripple modern buildings, the thermal resistance of the timber improved. Heat leakage slowed, microgaps closed, energy retention increased. The material behaved in a way modern insulation does not. This wasn't luck, and it wasn't accidental craftsmanship. The evidence pointed to intentional design structures conceived not as static shelters, but as coordinated thermal systems. Floors worked with hearths, walls interacted with roofs. Airflow, moisture, and heat were managed together, not separately. Nothing functioned alone. Every element served a role in a larger system that balanced warmth, ventilation, and humidity without external power or mechanical control. Long before blueprints, long before engineering terminology, these buildings operated on principles modern science would only later formalize. Centuries before the phrase existed, the Vikings had already built passive thermal architecture, not by theory, by survival. The secret of Viking winter survival began long before a single wall was raised. Construction did not start with tools or measurements. It started in the forest. Vikings did not harvest trees at random. Dendrochronology, tree ring analysis reveals a pattern of deliberate selection. Pines and spruces were taken from the harshest environments available, high latitudes, wind-scoured slopes, regions where growth was slow. Winters were long, and survival demanded adaptation. These trees grew differently. Exposed to extreme cold, they developed dense cellular structures reinforced with resin. Growth rings tightened, internal pathways narrowed. The wood became naturally resistant to moisture and heat loss before it was ever cut. But selection was only the first step. After harvesting, timber was submerged in near-freezing water for entire winters. Not days, not weeks, months. Modern materials science now confirms what Viking builders understood intuitively. Prolonged cold soaking alters wood at a cellular level. Cell walls compress, capillary pathways shrink. Moisture movement is restricted. Thermal resistance increases by as much as 30% in controlled tests. And then comes the detail that still unsettles modern engineers. As temperatures drop, this treated wood contracts in a specific way. Instead of opening gaps, it seals them. Microscopic joints tighten, seams close, air leakage decreases. The colder the environment becomes, the more secure the thermal envelope grows. Stress improves performance. Modern buildings behave in the opposite way. Materials expand and contract unpredictably. Seals fail. Heat escapes faster, precisely when it's needed most. Viking houses did not leak under pressure. They locked warmth in. This was not primitive construction. It was material engineering executed without formulas, without laboratories, guided by observation, repetition, and survival. They didn't just build with wood. They engineered it. Beneath the packed earth floors of Viking longhouses, archaeologists expected to find nothing more than compacted soil and scattered debris. What they discovered instead rewrote the understanding of early northern architecture. Using ground-penetrating radar, researchers detected hidden patterns beneath the surface, networks of narrow channels, carefully placed stones, void spaces arranged with intention. At first glance, they resembled primitive foundations. They were not. These structures were not designed to hold weight. They were designed to hold heat. At the center of the Longhouse, hearthstones absorbed thermal energy as fires burned. Dense and carefully selected, these stones stored heat slowly and released it even more slowly. Long after flames faded, warmth continued to radiate, sometimes for 10 to 12 hours long into the polar night. That heat did not rise and vanish. It moved. Warm air traveled beneath the floor, guided through shallow channels and cavities, spreading evenly across living spaces. Walls absorbed and reflected that warmth back inward. Drafts were minimized. Cold pockets disappeared. The floor itself became a source of heat, not a barrier against it. This was not accidental airflow. It was controlled distribution. What modern engineers would later call radiant heating was already functioning here without pipes, without pumps, without metal, without moving parts, no switches, no controls. Just gravity, stone, air, and fire working together. The result was steady, body-level warmth rather than harsh bursts of heat near the ceiling. Smoke dispersed without stealing energy. Moisture evaporated gradually instead of condensing into ice. In Northern Europe, this may be the earliest documented radiant floor system ever built, not designed on paper, designed by experience. When fire was scarce and fuel precious, nothing could be wasted. Every ember mattered, and Viking builders ensured that heat, once created, stayed alive long after the fire went dark. The roof revealed the next shock. For centuries, roofs were assumed to be passive, simple barriers between humans and the sky. But Viking longhouses tell a different story. Hidden within layers of turf, timber, and thatch were ventilation systems that responded automatically to what was happening inside the building. No handles, no switches, no human intervention. As fire warmed the interior air, that air expanded and rose. Subtle channels embedded within the roof structure opened naturally, allowing smoke and excess heat to escape. When temperatures dropped, the process reversed. Air contracted, openings narrowed. The system sealed itself. The building adjusted in real time. This self-regulating behavior prevented smoke from accumulating without stripping the room of warmth. Carbon monoxide levels remained low. Condensation, one of winter's deadliest threats, was controlled before it could freeze into walls or drip back onto living spaces. Modern buildings struggle with this balance. Too much moisture, and walls rot or freeze. Too little, and lungs suffer, fires burn unpredictably, and air becomes dangerously dry. Viking roofs managed both. Humidity stayed within a narrow, survivable range. Heat was conserved. Fresh air entered only when necessary, and only in the amount required. The system functioned continuously, day and night, regardless of weather or human error. The house did not need constant attention. It responded on its own. What emerged was not just shelter, but a responsive environment, one that behaved less like a structure and more like an organism. It sensed internal conditions. It adjusted its behavior. It protected the people inside without demanding their constant effort. The Viking longhouse was not a static object. It was a living system, quietly thinking, breathing, and adapting as winter pressed in from all sides. At sites like Jarlshof and other North Atlantic settlements, archaeologists began to notice something that changed how Viking homes were understood. The interior of the longhouse was not thermally uniform. It was intentionally divided into zones, each with a different climate, each serving a precise purpose. Closest to the hearth, living spaces remained warm and stable. This was where people slept, worked, and gathered during the darkest months. Body, heat, fire, and radiant floors combined to create a survivable core where life could continue even during prolonged cold. Move farther away, and the temperature shifted. Mid-zones remained cool but consistent, ideal for storing dairy, grain, and fermented foods. These areas avoided freezing while slowing spoilage, allowing supplies to last deep into winter. At the outer edges of the structure, temperatures dropped even further. These spaces were deliberately cold, functioning as natural refrigeration. Meat was preserved without ice. Nothing rotted. Nothing was wasted. This was not about comfort. It was logistics. Isotope analysis of preserved organic remains reveals controlled fermentation processes occurring throughout winter months. Nutritional value increased. Food became more digestible. Calories were preserved when fresh resources were unavailable. The Longhouse didn't just protect food, it transformed it. What emerged under one roof was a complete survival system: heat management, food preservation, and human life operating together. Each zone supported the others. If one failed, the entire system was at risk. The Viking Longhouse was not simply a place to hide from winter. It was an ecosystem engineered to sustain life when the outside world offered none. None of this functioned on instinct alone. The Viking Longhouse did not survive winter simply because it was well built. It survived because knowledge was treated as a survival weapon, taught, guarded, and enforced with absolute seriousness. Archaeological evidence points to strict systems of knowledge transmission. Children did not only learn how to carve wood or sharpen tools, they learned how heat moved through a space, how smoke behaved, when to open vents, when to seal them, how long a hearth should burn, how moisture could quietly turn deadly. These lessons were learned through apprenticeship, repetition, and correction. Watching elders manage fire and air was as important as learning to hunt or sail. There was no room for improvisation. Runic carvings, found on wooden elements and tools, suggest forms of technical notation marks that likely recorded measurements, sequences, or seasonal instructions. Oral traditions reinforced these rules with stories that emphasized consequences, not heroism, because mistakes were not theoretical. Closing a vent too early could trap carbon monoxide. Misjudging humidity could rot food or freeze walls. A poorly managed hearth could poison an entire household before morning. There were no second chances. This was not folklore passed down for comfort. It was engineering discipline enforced by necessity. Every generation inherited not just structures, but systems and the understanding that survival depended on precision. Knowledge was not optional. It was the difference between waking up and never waking at all. Today, the Viking Longhouse is no longer studied as a historical curiosity. It is studied as a solution. Across the modern world, engineers working in the most hostile environments on Earth are looking backward for answers. Antarctic research stations, military shelters in the Arctic Circle, architects designing passive houses meant to survive grid failure. Again and again, the same structures appear in their research, reconstructed Viking longhouses. The reason is simple. When energy systems fail, Viking systems do not. There is no electrical grid to collapse, no fuel supply to interrupt, no external input that must be maintained for survival. Modern buildings are efficient only as long as power flows. When heating systems shut down, interiors become uninhabitable within hours. Pipes freeze, air turns toxic. Temperature drops faster than the human body can adapt. Viking structures behave differently. They were designed to function indefinitely, using materials that responded to cold rather than resisting it. Heat stayed where it mattered. Air regulated itself. Moisture remained controlled. Life continued without switches, screens, or emergency generators. Climate researchers now classify these designs as successful examples of long-term human adaptation to extreme environments, not short-term shelter, not emergency housing, but sustainable systems capable of supporting communities through repeated winters without collapse. This shift in perspective matters because it reframes Viking architecture not as primitive, but as resilient, not outdated, but instructive. In a world facing energy uncertainty and climate instability, these structures offer more than historical insight. They offer guidance. This is not nostalgia. It is not romanticism. These are blueprints tested by centuries of winter and still relevant when modern systems fail. So here's the question that lingers. Would you trust your life to a smart building that shuts down when the grid fails? Or to a structure designed by people who knew failure meant death? The Vikings didn't conquer winter by overpowering it. They listened to it, adapted to it, turned it into an advantage. At Primal Heritage, we don't look backward to romanticize the past. We look backward to understand what worked when survival was non-negotiable. Because sometimes, the most advanced solutions aren't new. They're the ones tested by centuries of winter and still standing. If this story changed how you see ancient technology, take a moment to reflect, share your thoughts, and join us as we continue uncovering the forgotten engineering that once kept humanity alive when nothing else could. Primal Heritage,